Okay, round three, triple integrals. So we've done Cartesian coordinates, which are nice because they're easy to work with and they're familiar to us, but the calculations become terrible with all those square roots and everything. And then we just talked about cylindrical coordinates, which are also, kind of nice for certain situations. If you have a cylindrical looking shape in particular, it can be quite useful. Naturally, the next thing we're going to talk about is spherical coordinates, which um, sometimes make the calculations easier, but it's much harder to remember how to convert to spherical coordinates. So, really, I mean, just kind of pick your poison here. What's going to be the least painful way of solving these things? Okay, so here we go. The final installment of triple integrals, spherical coordinates. So let me just remind you what a spherical coordinate is. So x, your x coordinate is given by rho times sine of phi times cosine of theta. Y is given by rho sine of phi sine of theta. And z is given by rho cosine of phi. What do all these things mean? Oh, I don't remember any of this stuff. Oh yeah, that's right. Okay, so rho is the distance that your uh, a point is from the origin, essentially. So if you draw a vector, let's go. Everybody remembers vectors from a million years ago, I hope. If you draw the vector from 0 to your point P, um, then the magnitude of that vector is what rho is. It's going to be a non-negative quantity, and this looks kind of cool, right? I don't know if you all have seen this before. I've got a bracket around infinity here. That is not a typo, folks. I do mean that rho could in fact be infinite here. It is not. It does not have to be a finite quantity, which is kind of exciting. Phi is an angle between 0 and pi, and I remember earlier in the year we kind of discussed this at length, why we don't go from 0 to 2 pi. So hopefully, remind yourselves of why that's the case. But phi is not ranging from 0 to 2 pi, it's only ranging from 0 to pi. And that is the angle between the z-axis and your vector. The vector, again, defined by the terminal point is at p, and it starts at the origin. Theta is the same theta from polar coordinates and the same theta from cylindrical coordinates. It's just the angle, in the xy plane between the positive x-axis and wherever your point lies. If you were to project it straight down, I should say. And theta is allowed to be anything from 0 to 2 pi. So I've got a nice little picture there to remind you, or just go back and watch my videos about spherical coordinates if you've forgotten all these things. Excuse me. When we talked about cylindrical coordinates, we talked about the fundamental surfaces. So let's discuss here the fundamental surfaces in spherical coordinates. So if rho is equal to c, some constant, some non-negative constant I might add, you're going to get a sphere of radius c. And actually, is it c, or it would be square root of c? Something to think about. Anyways, so you see in the picture here on the left, you've got a bunch of spheres inside of each other, so you get a family of spheres. If theta is equal to c, just like in cylindrical coordinates that we just did, you get this a plane or a half plane. And when phi is equal to c, interestingly enough, you get a cone. So you see here, if phi is equal to pi over 6, you get kind of a narrower cone. And if phi is 2 pi over 3, you get a wider cone that's opening downwards for some reason. Something to think about, I guess. So these are your fundamental surfaces for spherical coordinates. When we change variables here, so you remember just a moment ago when you were watching your cylindrical coordinates, dv, so let's actually go all the way back to Descartes. So Cartesian coordinates, your volume is given by dx, dy, dz. And then in cylindrical coordinates, this is given by r, dr, d theta, dz. So it got a little bit more complicated. We had to remember to put this r in there. For spherical coordinates, things get crazy. dv, yeah, it has the d rho, d phi, d theta. It has, d each of your variables. But the extra part here is just lunacy. You have to multiply this by rho squared sine of phi. Where have we seen that before? Where is this looking familiar? Where was r looking familiar from before? Perhaps you all remember a long time ago, in a galaxy far, far away, that you had to calculate the Jacobian of certain matrices. Look back, and I don't remember what problem set it was. Problem set, like, I don't know, 9-ish is jumping mind. But in one of those, you calculated the Jacobian of some matrix of some different things, and you I believe found rho squared sine of phi coming out of that. I wonder if that has anything to do with what's happening here. It has everything to do with it. Or if you prefer geometry, you can kind of draw this picture. So this is what like a unit of volume looks like. So for some reason, and I don't understand why because I don't do geometry, this distance right here is rho sine of phi times a change in theta. And this distance right here is rho times a change in phi. And this distance here, I understand that one is a change in rho. And if you multiply all those together, then you're getting rho. Oh, I think there should be a squared here. Where's the other sign coming from? Oh no, that is just saying one of them. What? I feel like this should be saying sine squared. I don't know. I don't know where this picture is from. But yeah, the volume of that, it's not a cube. It's kind of like a sector, but in 3 dimensions. It's weird. The volume of that is rho squared sine of phi times a small change in rho times a small change in phi times a small change in theta. Okay. So just again, just like we always have to remember to put it in R when we use polar coordinates or cylindrical coordinates, we always have to remember to put in a rho squared sine of phi whenever we deal with spherical coordinates. Yuck. Okay, so let's do a fun exercise. Let's find the volume of a sphere with radius R. You should know the answer already to this, but let's prove it. And by the way, if you try to do this in rectangular coordinates or even cylindrical coordinates, it's going to get ugly fast. So here, again, we're just finding volume, right? So that means that my integrand is 1. However, because I'm switching to spherical coordinates, my new best friend, I need to remember to put the rho squared sine of phi in there. So that actually becomes our integrand. It's only multiplied by 1, though, right? 1 is really what we're integrating, but that's just something that we need to include here, this rho squared sine of phi, in order to make the calculations work out. So you notice that I'm starting off with rho, and rho is going to range from 0 to r. Rho is my distance, right? So I'm starting off at 0, and I'm going all the way out to the radius, to the outermost point. Phi, there's no limitations on phi, so I'm just going to use the full range from 0 to pi. Remember, it doesn't go to 2 pi, it only goes from 0 to pi. And then theta is again around allowed a full range of motion, so that's going to go from 0 to 2 pi. Jose, okay. So convince yourself that this is the right setup, and let's plow through this. If you take the integral with respect to, I'm looking at the inner integral here. You take the integral with respect to rho, I'm getting rho squared over 3 times sine of phi, which I can evaluate from 0 to r, and I'm getting r cubed over 3 times the sine of phi. Then I can iterate that very easily with respect to phi, and I'm getting, negative cosine of phi, which I'm evaluating from 0 to pi, and that's going to give me 2, sort of miraculously. So my integrand now is just 2r cubed over 3, and I'm integrating this with respect to theta, but there is no theta there, so I basically just multiply this answer by 2 pi, and voila, we get 4/3 pi r cubed, which hopefully you all know is the volume of a sphere. Such magic that happens here. Okay, so that was too easy. That was too simple. Let's do something more complicated. Let's evaluate this integral. So x squared plus y squared plus z squared raised to the negative 3/2 power. I want to integrate that essentially over this region D, where D is defined by the first, it's a region that's only living in the first octant, and it's between the sphere of radius 1 and the sphere of radius 2, both of which are center of the origin. So from the picture here, I hope you can kind of see what's happening. Our region over which we are integrating is a 3-dimensional region, right? It's this area that's it's basically just an eighth of a sphere, but it's going from 1 to 2 units away from the origin. So we've got kind of like a spherical shell, but only an eighth of it. It's very crazy stuff. And by the way, integrating on over top of a 3-dimensional thing is going to give you a 4th dimension, right? So we're going into the 4th dimension here. I have no idea how to visualize what this is representing exactly, but we can still do the math, which is, I think, pretty exciting. So this problem, since there are spheres involved, is just screaming, use spherical coordinates, and that's, of course, what we're going to do. My integrand, in this case, is, so I've got x squared plus y squared plus z squared, which you will recall that just is rho squared. So rho squared is equal to x squared plus y squared plus z squared. And so I'm just going to substitute this whole thing in parentheses here with rho squared. And that's kind of nice because it's being raised to the negative 3/2 power, so that just becomes rho to the negative third, which is kind of nice. But then you always have to remember to multiply by this, extra term here, this extra thing that's coming from the Jacobian, rho squared sine of phi. And so what we're going to get at the end of the day is just, rho to the, negative first. So in other words, we'll just rho to the negative first sine of phi. That's going to be my complete integrand here. And I'm going to integrate this. Let's do rho first. And so rho is my distance from the origin, and so that's going to range from 1 to 2 because I'm in that shell, right? I'm in this shell from 1 unit away to 2 units away. Then I'm choosing to do phi. You can do this in any order you want. It doesn't matter. You do phi, since I'm only living in the first octant, my angle is going to go from 0 to pi over 2. And similarly, theta is also going to range from 0 to pi over 2, again, because I'm just only in the first octant. Okay, so, hopefully you're taking a minute or two here to convince yourself that this is the correct integral to set up. And from this point, this one's not too bad to calculate by hand, but I don't know, I just wolfram it, and I got pi times the natural log of 2 divided by 2, which I don't know if that seems reasonable or not, because if we were talking about units here, if we were talking about units here, this would be like, I don't know, inches to the 4th power. It's bigger, it's a higher dimension than cubic inches. It is whatever, I don't even know if there's a word for beyond cubic, I guess. Quartic inches? Is that a thing? I don't know, let's make it a thing. Okay, one last example here. I thought with the Death Star in the background this would be a good thing to do. I scream, you scream when we see the Death Star coming. But actually this is going to be a nice problem because we're going to find the volume of an ice cream cone. Very exciting stuff. So imagine that you have a cone, and then there's a sphere that is on top of that cone that's tangent to all points around the cone. If you just kind of find the region in between those, that's going to be exactly this ice cream cone shape. Hope you all agree with this. So I want to find the volume of this region that's lying inside of the cone, and this cone I'm defining as phi is equal to pi over 6. You remember that when phi is equal to a constant, that's giving you a cone. And I want this to be living also inside of the sphere. This particular sphere is rho equals 4. Okay, so here is basically the answer, right? I mean, so the volume means that I'm finding the volume, so that means the integrand is just 1. But just remember to put the rho squared sine of phi in there. So crucial. Just like you never forget to put the r in the other in cylindrical and polar coordinates, you never forget to put rho squared sine of phi in here. Okay, so phi itself is ranging from 0 to 4, and that's because we're inside of this sphere, right? We're ranging anywhere from 0 to 4 units away from the origin. Phi is ranging from 0 to pi over 6 because, I mean, the cone, when we talk about, we say that the cone is phi equals pi over 6. If we're trying to find the volume, it's, there's a solid, so it's ranging anywhere from 0 to pi over 6. And then theta, of course, we're doing a full rotation here. This cone, goes all the way around, as does the sphere. So theta is going to range from 0 to 2 pi. And so there's the setup. Again, you can change the order around if you like, but I kind of like this one. Wolfram it or do it by hand if you're feeling particularly crazy. And I'm getting something like 64 pi over 3 times 2 minus root 3, which looks pretty gross, but that's the exact answer. You can round that off to some decimals if you'd like, but that is the volume of my ice cream cone. So assuming that my cone itself is paper thin, I can hold a good amount of ice cream in there. That makes me excited. Okay, great. So if you take nothing else away from this, use spherical coordinates to calculate volumes of ice cream cones, and use cylindrical coordinates to find volumes of cheesecake. And that will serve you very well. Okay, great. Well, you've made it through all 3 videos about triple integrals. I hope you've enjoyed yourself. and I will see you all very soon.